Jain to all. I am Samender Singh, Assistant Professor in the CSC Department, AKGEC Engineering College, Ghaziabad. I am in Computer Science Department. I am taken compiler design. Today I will discuss about what is parsing techniques. This is our topic. Parsing techniques. Let's start. Along this, we will discuss about syntax analyzer, what is parser, context-free grammar, parse tree, left recursion, left factoring. Let us start the topic. Syntax analyzer. As we know about compiler design, it having a number of phases. Syntax analyzer is the second phase of the compiler. So it will create syntactic structure of the given source program. Syntactic structure is mostly a parse tree. What is parse tree? It's a hierarchical structure through which we represent the given string after validation. After validation means it will validate the given string that it is right or wrong according to the syntax of the programming, and this is done by means of syntax-free grammar that will tell us the rules of the grammar through which we design any programming language. Or we can say the context-free grammar will tell us the given string is valid or not. All rule about any validity of the given string is listed in context-free grammar. Syntax and analyzer, also known as parser, check whether a given source program satisfies the rule implied by the context-free grammar or not. I already tell you. If it satisfies, then parser creates the parse tree of the program. Otherwise, parser gives the error message. That means syntax analyzer have two core functions. First function, it will satisfy if the given string is valid, then it will create parse tree. Otherwise, it will create error message. And next, context-free grammar. It gives a precise syntactic specification of a programming language. And also the design of the grammar is an initial phase of the design of the compiler. A grammar can be directly converted into a parser by some tool like Lex, AKGEC. These are the popular tools through which we convert parse. Now it's a block diagram of the parser. As I already told you, it is the second phase of the compiler, works on the stream of the token that we get from first phase, lexical analyzer tokens. We are getting, after getting first token, it will send request for getting next token, and through these tokens it will generate parse tree. So parser, we categorize parsers into two types: top-down parser, bottom-up parser. In the top-down approach, we starting with starting symbol up to leaves, where leaves represent symbols, or we can say terminal symbol. And bottom-up parser, it's a reverse of the top-down parser. So in bottom-up parser, we starting from leaves and up to start symbol. I already told you bottom-up parser is reverse to the top-down parser, just like this one. Suppose the given string is this id asterisk id plus id. So top-down parser will create from starting to start symbol. Suppose start symbol is this one. Number of production rules we have, just like this one. Suppose this is. So we are starting with E. E, then E plus E, then E asterisk E. Again, this is ID, this is ID, and this is ID. So this is our parse tree, in which we are starting with the start symbol up to terminal symbols. These all are terminal symbols. ID, asterisk, plus ID. These all represent as a terminal symbol of the grammar. This is the production rule through which we derive by means of top-down parser, in which we start with the starting symbol up to leaves. Leaves represent as a terminal symbol. When we talk about bottom-up parser, it's reverse process to top-down parser, in which we are starting with the given string, and after number of reduction, here we are using operation reduction. Reduction is what? We are right hand side symbols up to we reduce to a single non-terminal. After number of reduction, we reach to starting symbol. This is just reverse process of top-down parser. So in this way, we are categorize the parsers into two types. First is top-down and second one is bottom-up. In both the parsers, we scan the input from left to right, one symbol at a time. So this is data structure, normal known as input buffer, that stores the string. The string is what? Suppose this is a string. So this is string storing one symbol. So in both the parser, we scan from left to right. Means first we scan this symbol, after that we scan this symbol, then we are scanning this symbol, and this process is continuing up to we are getting the end marker of the input string. Generally, we denote end marker by $sign. So this is the process that will accomplish in both the parsers, whether it's a top-down parser or in bottom-up parser. We are having two words. First is LL1. It is for top-down parser, where L means again left to right, scanning of the symbol from left to right in the given input buffer. And second L is what? Second for leftmost derivation. So in top down we are using leftmost derivation approach, and in bottom up parsing we are using R. You can see first symbol in both the parsing is same, that is L, which denotes left to right scanning of the given symbols, or we can say string, and R represent as a rightmost derivation in case of bottom up parsing, and L, that is leftmost derivation in top down parsing. This is the core difference between these two parsing. Now next topic is context-free grammar. It's one of the type in the grammar. As we already know, Chomsky hierarchy gave the four categories of grammar. One of that is syntax-free. Inherently recursive structure of a programming language are defined by a context-free grammar. In a context-free grammar, we have terminals, non-terminals, and finite set of production and a start symbol. As we know, V, T, P, S. These are the four tuples of any grammar. When we talk about context-free grammar, it is differ by means of its production construction. So where terminals represent in compiler as a tokens specified, or we can say these are the special kind of symbols used in a particular language. So these are terminals. Next, what is non-terminal? These are the syntactic variables through which we are apply reduction, or we can say we are driving a number of we can drive a number of strings. Then we have production rules. Through this rule, we are able to validate a given string, or we can say anything which we are using in compilation. This is a kind of productions we found in context-free grammar. That is, in left-hand side, we always find a single non-terminal, and in right-hand side, we have alpha. That simply means VU. V union T, that is variable union T asterisk. We can say any possible combination of variable and terminals, including epsilon. And 4 tuple is start symbol, one of the non-terminal through which we generally start our productions, or we can say our derivations. We have a example. We are starting symbol E, have number of productions. That first production is E gives E plus E, in which we have terminal. If we talk about this grammar, then we are number of terminals. First of that is plus sign, then we have minus operator, then we have asterisk operator, then divide operator, then unary U minus, we can say it's a unary operators. It is different from this one. This is binary operator, this is unary operator. These all are represent as a terminal symbol in the given CFG. Again, in the second, we have starting bracket, closing bracket, and finally in the final production rule, we have ID as a terminal symbol. And we have just one non-terminal, that is capital E. It is non-terminal, or we can say it's a variable of the grammar. So, derivation point of view, we start with the first production rule. E gives E plus E. That means E plus E derive from this one, E. We can replace E by this one. To able to do this, we have to have a production rule, this one, which we have in the given production rule. Suppose this one. Again, we are replacing this to this one by means of the last production rule in the previous one that you found here. This is the last production rule. We are using this to drive first non-terminal to ID. Again, in the second, we are convert to this one. Now we find sequence of symbols in which we have only terminal symbol. So this is known to be string. So string is a collection of terminal symbols. So we can say sequence of replacement that we done. First we replace E to E plus E, then we replace this E to ID, then we replace this E to ID. So we are getting number of replacement. So sequence of replacement of the non-terminal symbol is called derivation. This whole process, step 1, then step 2, then step 3, is known as derivation of what? Of a string from given start symbol. So this is complete procedure in which we starting with the start symbol up to the given string. Here string is ID plus ID and start symbol is capital E. In general, a derivation step is this one, alpha A beta and alpha gamma beta. If there is a production alpha gamma, alpha gives gamma. In our grammar, alpha, beta are always V union T asterisk. These are all possible combinations of variable and terminal symbols, just like this one. So we have alpha 1 again to alpha 2 first translation, or we can say the replacement. Then we have number of replacement up to we are getting a alpha n. So alpha n derives from alpha 1 through a number of steps. So if we are getting our given string in single step, so we can say derives in one step. If we do same in more than one steps, or we can get the same only one zero derivation. So we can derive by one step, in zero step, or more than a step, or derive in one or more steps. These are the possibilities through which we are getting our string. Now, CFG. What is CFG? Context-free grammar. So we have a language of the given grammar generated by which is a set of sentences. So any language supported by the CFG is simply set of sentence in which sentence represent the string derived by means of the CFG. Again, sentence of is a string of terminal symbol, I already told you. S is the start symbol of the Z, then omega is the sentence of LG if S we are starting with the starting symbol up to omega, where omega is a string of terminal symbols. We can say if we found any string means collection of terminal symbol that we derive after apply valid production rule of the given CFG. If it happened, then we can say it's a sentence of the language specified by their CFG. G is a context-free grammar and LG is the context-free language. So, language supported by context-free grammar is known as context-free language. So, we can say two grammars are equivalent if they produce the same language. We already know this. Suppose this one is starting with the start symbol up to alpha. If alpha contains non-terminal, it is called sentential form of Z. And alpha does not contain non-terminal, it is called sentence of Z. In this one, suppose in each replacement, we are finding these intermediate form in which we have combinations of terminal and non-terminal. So what we called it, it's a sentential form. Just this is sentential form of G. And if it contain all, it does not contain non-terminal, only contain terminal symbol, then it is known as sentence, or we can say string of the G. Now again we have a simple example of derivation starting with E. Then we are using unary operator grammar. Then again just we are using another production rules to convert E to E dash. In first we are using E gives minus E. And in the second we are using E gives this one, second replacement. In the third replacement we have E plus E. In the fourth we are converting this to this one, and final we are converting this to this one. So this is first. You can see in each replacement we are choosing leftmost symbol, or you can say leftmost derivation. First only one symbol, this is leftmost, or we can say rightmost. In the second, it is also that are going to expand. It is again we have single, no need to find. And here we have two different variables in which we can easily find which one is leftmost or which one is rightmost. We can see this is in left position and this is in right position. So we are converting the leftmost symbol to ID. Again, we have only one symbol and we are converting to this one. So this approach in which we are choosing variable that are placed in leftmost position. So this derivation is known to be leftmost derivation. You can see if we always choose the leftmost non-terminal in each derivation step, this derivation is called leftmost derivation. And second approach, what we can use, if we always choose the rightmost non-terminal in each derivation, then this derivation is called rightmost derivation. So these are the two approaches we found in the derivation. First is known as leftmost derivation, in which we always choose variable which are going to reduce, which are going to expand, will always place at leftmost position. And in the rightmost derivation, we always choose the variable that are placed in the rightmost position. In the next, we have leftmost and rightmost derivation example. You can see up to here almost seems same. Here you can see we are using leftmost variable and here we are using rightmost variable. So this is known to be leftmost derivation and this is rightmost derivation. Again, we will see that the top-down parsers try to find the leftmost derivation of the given source program, and we will see that the bottom-up parsers try to find the rightmost derivation of the given source program. So, if we are using this approach, which parser uses which derivation? So, we can say this is bottom-up parser. This approach used in bottom-up parser and this approach is used in topmost parser. Next is what is parse tree? It's a hierarchical structure of the string. Again, inner nodes of a parse tree are non-terminal and leaves of the parse tree are terminal symbols, just like this one. These are the productions. We replaces E by minus C by using our appropriate production rule. So we can convert by means of single tree hierarchical structure in which we are starting with E. So E is replaced by two symbols. First left symbol is minus, or we can say unary minus, and second symbol is E. So this is converted to this one. And again, this is converted to this one, again, in which we are finding non-terminal, which are going to expand. So E is going to expand to this one. First E replaced by minus E, and this E again replaced by starting brace, then E, then closing brace. So this is parse tree gets deeper. In first already got, and this is further expand in this by means of second production rule. E expand to starting brace, then E, then closing brace. And again, this E further expanding this way, E plus E. And finally, this converted to EI replacement, and finally this I going to this one. So this complete structure or hierarchical structure is known as parse tree. It is parse tree. So which approach we are using in this derivation? We can easily find here single terminal, again single terminal, again single terminal. Here we are getting left symbol. So this is leftmost derivation. In which parser we are using leftmost? That is top-down app, top-down parser. We starting with the start symbol up to leaves. Where is leaves? These are the leaves. Minus, then starting brace, then ID, then plus, then again ID, then closing brace. These all symbols represent as leaves, and it is also symbols. These are the sequence. This is first symbol, then second symbol, then third symbol, then fourth symbol, then fifth, then sixth. So in the tree leaves we are counting from left to right. First symbol match, second symbol match, third symbol again match, fourth symbol again match, fifth symbol again match, sixth symbol again match. This is our required parse tree. So this is derivation, or we can say leftmost derivation. It is generally used in top-down parser. Next topic is ambiguity. You know the meaning of ambiguity. When we have two meaning of a word, process is known to be ambiguity. This logic is applied to our grammar. Grammar is what? Suppose a grammar produces more than one parse tree for a sentence or a string, then the grammar is known as ambiguous grammar. Suppose we have a string ID plus ID asterisk ID. We are forming parse tree. So we have two ways. In first way, we are getting this one, match to first symbol, again we have, then plus, again we have, third, fourth, fifth, all we have, correct. And in the second approach, we again find first symbol match, second symbol again match, third symbol again match. So this is also a parse tree of this one. If we found more than one parse tree of a sentence or a string, then this grammar is known to be ambiguous grammar. I think you all understand this one. Next is, for the most parser, the grammar must be unambiguous. This is first condition. Otherwise, parser fail to construct any parse tree. Ambiguous grammar means we have unique selection of the parse tree for a sentence. We can make a single parse tree for a single string. There is no possibility to generate more than one parse tree of the given string. Again, we should eliminate the ambiguity in grammar during the design phase of the compiler. Our first step. Ambiguous grammar should be written to eliminate the ambiguity. Unambiguous should be there. We have to prefer one of the parse tree of a sentence generated by ambiguous grammar to disambiguate that grammar to restrict to the choice. Our choice should be unique. Suppose this is our example. We have given three productions. Here, starting symbol or variable is a statement, and these are the first production rule, that is, if expression then statement. Second production, if expression then statement, else statement. And third one is other statement. So these are the statement, these are the production rule of the grammar. And this is the string we have given, in which we have if even means expression 1, then if expression 2, then this is statement 1 as statement 2. So we are converting these to possible parse tree. We are starting with the start symbol statement. We are using second production rule, that is if expression then statement else statement. In this one again we are starting expression to even other statement. Again, in the second variable, we are expand it to by means of first production rule, that is statement to if expression then statement. In this variable, we are convert E2, and this statement is S1, and this statement is S2. So this is what we are getting our string, given string. If even, yeah, match, then if E2, then S1, else S1, else S2. So this is right product pass tree of the given string, and this is also achieved by means of another way. Let's see, in which we are start with our start symbol, where we are using first production rule rather than second. In this case, we are using first production rule, and through which we are able to find solution, that is if E1, then if E2, then S1, else S2. So this is also achievable. Means we have two pass tree of the given string. That means this grammar is a case of ambiguity, or we can say this grammar is ambiguous grammar, since we have more than one pass tree of the given string. We prefer the second pass tree, else matches with just if. So we have to disambiguate our grammar to reflect this choice. The unambiguous grammar will be, this is the solution of previous one, in which we have three productions. We convert it to unambiguous grammar, in which what we do, we convert this statement, this start symbol, to two new variables. First variable is matched statement, second is unmatched statement. Then for matched statement, we have two productions, that is if expression, then matched statement, as matched statement, and second is other statement. And second variable, we have two different productions, that is if expression then statement, if expression then matched statement, else unmatched statement, through which we convert to unambiguous grammar. Means through this grammar we are unable to find more than one pass tree of the given string. Another way to make ambiguous grammar to unambiguous grammar by means of precedence. Where we apply precedence, this is applied to operator, and in operator means we are applied to terminal symbols. Operators are generally terminal symbols if we talk about compiler. So ambiguous grammar, because of ambiguous operators, can be disambiguous according to the precedence and associativity rules. If we talk about this grammar, we have number of operators, just like plus, then asterisk, then power operator, and then, so these are the three operators. Precedence wise, highest precedence is power operator, then asterisk operator, and last one is addition operator. In the first power, associatively right to left, means if we found two power operator in the same statement, we choose first right. In the same manner, left to right in case of asterisk and plus. So we convert this to this one. You can see plus is a left to right, means first we are operate leftmost plus operator. So we are convert second terminal to a new variable. This is how. E plus T, and this T is also equate to E, and this T have next level of precedence. Yeah, we can say this will generate new productions for next label, since this is least precedence over asterisk and power operator. So we are starting with this one. After that, we are choosing asterisk operator, and finally we are in the final production we are using power operator. And you can see in first two cases we are unbound to the rightmost position, since these are left to right, left to right associativity. But when we talk about power operator, it is right to left, so we are rightly unbounded this one. So this is how we can convert ambiguous grammar into unambiguous grammar. Next. So this is all in this session. We will continue to next session. So, thank you very much to all.